Welcome to the deep dive. Today we're looking into, well, a kind of cosmic detective story.
Mm-hmm.
Our investigator isn't, some person,
Yeah,
but a space telescope, Gaia.
that's right.
Its main job, mapping stars,
Oh,
billions of them, with amazing accuracy. But the really cool part we're diving into is how this star map is now finding planets around those stars.
exactly. Gaia's been charting positions, movements for over 1 billion stars for years now. It's like the ultimate cosmic address book.
Yeah.
But yeah, as we'll get into, that precision, it's opening up a whole new way to actually find exoplanets, planets outside our solar system.
Right. And you might think of Gaia as just the star mapper, which, okay, is a huge part of its mission.
Sure is.
But in this deep dive, we'll see how its incredibly fine measurements using this technique called astrometry are becoming a really powerful exoplanet hunting tool.
Yeah, it's pretty exciting.
I mean, we already know about, what, over 5,000 exoplanets from other methods?
Yep, around that number.
But Gaia's approach, it promises to show us a whole different group of these worlds, ones we basically haven't been able to see before.
And it's worth remembering, the whole idea of planets out there was just speculation not that long ago, really.
That's right.
It's only in the last maybe few decades we've even had the tech to spot them. The first confirmed one around a star like our sun was 1995.
Wow, yeah.
Since then, it's been this race to find different ways to detect them. Each method gives us a slightly different piece of the puzzle.
Okay, so before we get deep into Gaia's technique, maybe let's just quickly recap. How have we been finding planets up till now? What are the main ways?
Well, the biggest winner, by far, has been the transit method.
Right.
That's where you look for these tiny, tiny dips in a star's brightness when a planet passes, right in front of it from our point of view.
Like a mini eclipse.
Exactly. NASA's Kepler mission was huge for that. Found the vast majority, like 3,500 or so, by mid-2022. Then there's radial velocity. That's looking for the stars wobble towards and away from us, caused by the planet's gravity pulling on it.
The Doppler shift thing.
Precisely. And there are others too, like gravitational microlensing, using gravity bending light and direct imaging, actually trying to take a picture, which is incredibly hard.
Okay, fascinating toolkit. So where does Gaia's astrometry fit in? You said it could find many more. How's it different?
So the thing is, transit and radial velocity, they're kind of biased, right? They're best at finding planets really close to their stars, or ones that happen to line up perfectly for a transit.
Right, makes sense.
Gaia's astrometry, though, it's really good for planets that are further out, and ones whose orbits aren't edge on to us.
Ah,
Think about it. A planet's gravity doesn't just pull the star towards or away from us, it also makes the star trace this tiny little circle or ellipse against the background stars.
like a tiny dance.
Exactly, a tiny dance. And astrometry is all about measuring those minute sideways movements super precisely.
Okay, here's where I find it really interesting. This idea, measuring the tiny wobble, it sounds so elegant, right?
Mhm.
But you also hinted it's been really hard historically for finding planets directly. Why? What's the catch?
Yeah, exactly. The concept's simple enough, but the actual wobble, even from a big planet, it's incredibly small. Especially for stars light years away. I mean, just minuscule.
Like how small are we talking?
Think about trying to spot, I don't know, a firefly buzzing around a porch light, but the porch light is in another city. It's that kind of scale challenge.
Wow. Yep.
Even earlier space missions like Hipparcos or Hubble's Fine Guidance System, which were amazing for their time at measuring star positions,
Right.
they mostly just help confirm a few planets found other ways, or maybe refine the orbits for a handful.
So they didn't really discover many on their own with astrometry.
Very few. Historically, if you look at NASA's exoplanet archive, there's really only one system listed as discovered solely by astrometry for a long time.
Only one out of thousands. That's stark.
Um,
Tell us about that one, though. What was it?
Yeah, it's an interesting one. DNSP 082303.1491201, bit of a mouthful. It was found by watching its 246-day orbit around this really low-mass, super cool star in L dwarf, pretty close by too, just 20 parsecs.
Okay. And the companion, planet size.
Well, that's the interesting bit. It's hefty, about 28 times Jupiter's mass.
Whoa. That's big for a planet.
It is. It's right on that fuzzy line between a really massive planet and what we call a brown dwarf, like a failed star. So even that first discovery kind of sparked debate. Is it a planet? Is it a tiny binary system?
So if past efforts struggled, what's different about Gaia? What's the magic ingredient?
It really just comes down to precision. Gaia's accuracy in measuring positions and movements for, over 1 billion stars, it's just on a whole different level, a completely different order of magnitude than anything before.
Like upgrading from binoculars to Hubble, but for position.
Something like that, yeah. It's a huge leap. And simulations, based on what we think planetary systems look like, they suggest Gaia's first 5 years could find something like 20,000 long period Jupiter-sized planets within 500 parsecs.
20,000.
Yeah, and maybe 50, even 70,000 if the mission goes for 10 years.
Good grief. That's transformative.
It really is. Suddenly, astrometry isn't just a niche thing. It's potentially a major player, finding planets we've mostly been blind to.
Wow. Okay. And this data, it comes out in chunks, right? These data releases.
That's right. Gaia Data Release 3, or DR3, came out in June 2022. That's based on 34 months of observations from mid-2014 to mid-2017.
Right.
It was actually split into two parts, EDR3 first, then the full DR3. And the key thing for planet hunting is that DR3 includes tons of detailed info on non-single stars.
Binaries and multiples.
Exactly. Systems where you can really see the gravitational dance between stars and potentially planets in those super precise movements Gaia measures.
Right. That makes total sense. Focusing on those binary and multiple systems is key then. Why is that so important for Gaia, besides just finding planets?
Well, studying these systems is fundamental, really. It tells us a lot about how stars form in the first place, how they evolve together. And it helps us characterize all sorts of companions, other stars, those brown dwarfs we mentioned, and yes, planets.
And we used to find binaries in other ways.
Oh, yeah, visually, just seeing two stars, or seeing the wobble in their combined light that's astrometric motion too, just less precise before, or through spectroscopy, seeing the spectral lines shift, or if they eclipse each other.
But Gaia can do a lot of this at once.
That's the power. Its accuracy in both position, astrometry, and brightness, photometry, lets it find and characterize loads of these systems all at once, across the whole sky, in a really uniform way.
And DR3, it really delivered on this, didn't it, for these non-single stars?
Oh, absolutely. There's a whole group in the Gaia Consortium Coordination Unit 4. Their job is basically wrangling the data for these non-single stars, plus solar system objects, galaxies. It's incredibly complex work.
I bet.
Yeah, there's a big paper by Arenu and colleagues that details it all. But basically, they sort the solutions for these non-single stars into different types.
Yeah.
Well, some where they could calculate a full orbit, others showing this sort of nonlinear motion, hinting at an orbit, but maybe not fully covered yet. Some suggestions for long-period spectroscopic binaries, and even cases where a star seems to move because its companion changes brightness.
And the numbers, you said they were huge.
Just staggering. DR3 has something like 800,000 systems where they have either orbital elements calculated or at least parameters describing the trend in motion.
800,000.
Yeah. Within that, about 130,000 are full orbit solutions, and over 300,000 showing that clear, nonlinear astrometric wobble. And remember, this is just from the first 34 months. Future releases will make these even better, refine the orbits, find more. The scientific potential here is just immense for understanding stars and systems.
How does that compare to what we knew before?
Well, just for context, DR3 has about 40 times more astrometric orbit solutions than, say, the big historical catalog of visual binary orbits.
40 times.
Yeah, it's a revolution. And importantly, the results line up well where they overlap with older data, like accelerations measured by Hipparcos.
Yeah.
Gives us confidence.
Okay, so the foundation is laid. Gaia's accuracy, the focus on non-single stars. Now, the payoff.
Yeah.
The first actual exoplanet candidates found just using Gaia's astrometry. This is it.
This is it, yeah. So these substellar companions, brown dwarfs above maybe 20 Jupiter masses, planets below that.
Right.
Astronomers have been looking hard with radial velocity for decades, but Gaia DR3 finally hit the sensitivity needed for astrometry to find lots of them. By seeing that tiny wobble...
And it tells us more than just it's there.
Crucially, yes. Gaia gives us the 3D orbit, the shape, the tilt, and the true mass. Not just a minimum mass like radial velocity often gives. That's a huge advantage for understanding the system.
So what did they find in this first pass? Any numbers?
The initial trawl through the DR3 data, by our news team again, flagged about 1843 potential brown dwarfs and 72 exoplanet candidates.
72 candidates right off the bat.
Yeah. And what's really interesting is only a few of those were already known, 10 brown dwarfs and 9 planets, mostly from radial velocity
So
surveys.
most are new.
Potentially, yes.
Yeah.
And for the ones that were known, the orbital periods Gaia measured matched the old RV measurements really well, which is great validation for the method.
Okay, and out of these candidates, you mentioned two were fully validated as brand new planets found only by Gaia astrometry. That's history.
Absolutely. These are the first ones, the proof of concept. One orbits a star called HIP 66074.
Okay.
This planet takes about 297 days to go around. Its orbit is a bit elliptical, and it makes the star wobble by just 0.21 milliarc seconds. Tiny. Its mass is about 7.3 times Jupiter.
Wow. And the second one?
That orbits HIP 28193, longer period, about 827 days, much more circular orbit this time. The wobble is slightly bigger, 0.25 milliarc seconds, and the mass is estimated around 5.3 Jupiters.
0.21. 0.25 milliarc seconds. I mean, my brain can barely process how small an angle that is to measure across interstellar space.
It's honestly mind-boggling, and get this. The smallest wobble for a candidate on their whole list was just 0.14 milliarc seconds. That's 140 microarc seconds.
Microarc seconds.
Yeah, it's like trying to see a human hair from London when you're standing in Paris. That level of precision.
Unbelievable.
And that candidate list, it also included that oddball DNSP object we talked about.
A borderline one, yeah.
And several planets already known from radial velocity, like GJ876, HD 114762, confirms Gaia can see those too. And interestingly, even some giant planets found orbiting white dwarfs.
Planets around dead stars.
Yeah, like WD 0141675. These are super interesting. Maybe they formed from debris after the star died or were captured somehow. Gaia's finding all sorts.
Yeah. You mentioned HE 104762 was on the list, one found previously. Our sources showed a visual of its orbit from Gaia data.
Yes, that was from Hall and colleagues. They did detailed fits for several systems, including HD 114762. It's a fairly bright star.
What did the visuals show?
It just beautifully maps out the star's tiny elliptical path on the sky as the planet orbits every 83.7 days or so. You can see the wobble directly from the Gaia measurements, and Gaia's parallax measurement pins down the distance accurately too. Seeing that visual confirmation is, well, it makes it very real.
It really does. It absolutely feels like we're watching a new chapter open up here. Astrometry finally arriving as a major planet-finding technique.
I think that's exactly right. These first validated Gaia astrometric planets, they really mark a turning point. After decades of, potential but real challenges, the technique is delivering. And it's finding things in a way that complements the other methods beautifully.
So stepping back then, what's the big picture here? Gaia's online as this powerful astrometric planet finder. What does this really mean for understanding the cosmos?
Well, it opens up a whole new parameter space, doesn't it? Astrometry is best at finding those longer period planets further out from their stars.
Right, the ones transit and RV might miss.
Exactly. So we're finally getting the tools to study systems that might be more like our own outer solar system, perhaps, or just different architectures altogether. And getting the 3D orbits and true masses, that's huge for testing our models of how planetary systems form and evolve. We get a much more complete picture.
And with potentially tens of thousands more planets coming from Gaia down the line, what big questions does that spark for you about planets out there?
Oh, so many. I mean, first, just the sheer diversity we're likely to uncover. We'll probably find system types we haven't even imagined yet that will definitely challenge our theories.
Yeah.
And it forces us to ask, how common are systems like ours, with rocky inner planets, gas giants further out,
Right.
or are other configurations much more typical in the Milky Way? It's going to fundamentally change our view of planetary prevalence and maybe our own place in it all.
So the final thought for our listener.
I guess it's just, what kind of truly weird and wonderful planetary systems are still hiding out there, waiting for Gaia's incredible eye to spot their star's tiny dance? That's the really exciting unknown.